Today, I'm really delighted to introduce my postdoc, Dr. Rachana Gangwani. She received her bachelor's of physiotherapy from Manipal Academy of Higher Education, India, and she's a licensed physical therapist both in India and in the US. She got her Master of Science in Rehab Science at the University of Illinois at Chicago. And then she enrolled in a doctoral program in human movement science at the University of North Carolina at Chapel Hill, where she was advised by Dr. Jessica Cassidy. And her research focused on the mechanisms that underlie neuroplasticity after stroke and in better understanding the interplay between motor and cognitive domains, which is great for us in our lab. She's been recognized with a lot of awards, including numerous scholarship awards, the Allied Health Science Achievement Award from the University of Illinois at Chicago, and the Department of Health Science Student Research Excellence Award from the University of North Carolina at Chapel Hill. So before we get started today, I want to remind some of you or tell some of you for the first time that we're trying a new thing, which is that we're really encouraging other postdocs and junior people to speak up and ask questions so that it's not the usual cast of characters in the senior staff who are asking a lot of questions. So please feel free. Today, Rachana will be talking with us about mechanistic and neuroanatomic bases of disparity between arm capacity and use post-stroke. Thank you so much. Round of applause.
Yay. All right. Thank you, Laura. So the topic of my presentation is mechanistic and neuroanatomic basis of disparity between arm use and capacity post-stroke. Before I start, I'm happy to answer any short clarification questions while I'm presenting, but any long conversational questions, I'm happy to take them at the end of my talk. So I would like to start by thanking the Shrier family for the generous support for this lecture series. You can also earn CME credits. Here is the information and code highlighted in yellow, and that's 44419. We have no financial relationships to disclose. And here are the objectives of this talk. By the end of this talk, you would be able to describe the phenomenon of use capacity disparity, describe assessments used to measure arm use in individuals with stroke, and list potential sensory motor and cognitive factors that could predict use capacity disparity after stroke. So I want to start by introducing this very complex problem of disparity in arm use in capacity after stroke. So arm weakness is one of the most common consequences immediately after a stroke, and it persists even in the chronic stroke stage. So a lot of you might be familiar with this ICF model here, which is basically a framework that outlines different levels of disability in stroke and ranges from body structure and function impairments, activity limitations, and the participation restriction domain. So in both stroke rehabilitation practice and research, a lot of us tend to focus on this body structure and function domain. So in the context of arm weakness, we primarily tend to focus on reducing the impairment of the paretic arm or enhancing the functional capacity of the paretic arm. Now, despite these efforts, improvement in capacity or reduction in impairment does not necessarily translate to how people use their arm in daily life activities or how they participate in their social real life roles. In fact, a recent clinical trial proved that in individuals with chronic stroke that underwent high-dose task-specific training, there was a significant improvement in capacity of the paretic arm, but none of the 78 participants that were included in the clinical trial showed an increase in arm use in daily life as measured by actigraphs. So in this work, we refer to this problem as the use capacity disparity, which is basically a gap between what a person can do with their arm, so their sensory motor capacity or capacity for activity, and how much they actually use their arm in daily life. Strikingly, about 40 to 80% of individuals post-stroke have the capacity to use their arm but fail to do so in real life. Now, despite how common this problem is, the mechanisms that drive this disparity are poorly understood. So I want to start by showing this example of how motor impairment alone does not entirely account for real-life paretic arm use. So what you're seeing right here are two participants, participant A and participant B. We have the upper extremity Fugl-Mayer scores, which is a 44 and a 45 here. Upper extremity Fugl-Mayer is a test of sensory motor impairment, ranges from 0 to 66. Higher scores indicate less impairment of the paretic arm. 44 and 45 are like individuals with moderate sensory motor impairment of the upper extremity. Now, despite having similar levels of impairment, there is a striking difference between how these individuals use the paretic arm in real life as measured by the activity counts in active graphs. So, motor impairment alone does not entirely account for how people use the paretic arm in real life. The significance of this disparity is highlighted by this data that shows that quality of life is associated with arm use rather than motor capacity of the arm. So there are very few theories that explain use capacity disparity or the factors that might predict it. Building on previous models that emphasize sensory motor deficits as factors contributing to arm non-use, we propose a theoretical model of use capacity disparity here as a problem at the cognitive motor interface. So as we know that stroke not only causes sensory motor deficits, it also causes deficits in attention and motivation. And these factors combined together could potentially contribute to this use capacity disparity. So I want to highlight this negative feedback loop here, where individuals with stroke, when they start using their paretic arm to perform activities of daily living, that seems to be more effortful, right, to use their paretic arm. It feels a little less rewarding and maybe even painful, leading to reduced use of that paretic arm. On the other hand, using the non-paretic or the less affected arm is potentially less effortful. It's more rewarding because they're then able to do the task, which leads to more use of the non-paretic or the less affected arm. Now, to test this theory, there was preliminary work done by Dr. Laurel Buxbaum and colleagues who investigated predictors of arm non-use in individuals with chronic stroke. This study examined 20 individuals with unilateral left or right hemisphere stroke and determined associations between sensory motor, cognitive, and psychological factors, psychosocial factors, and how they relate to arm non-use post-stroke. The hypothesis of this study was that beyond motor capacity, cognitive and psychosocial factors will predict arm non-use post-stroke. In this study, arm non-use was measured through this assessment called as the actual amount of use test. And we measured something called as a non-use index. And this is something that will keep coming up in this talk. So the AUT, or the actual amount of use test, is a test where participants perform 14 different tasks in two conditions. The first is a spontaneous condition where they're not really given any instructions. They just perform the task that they are being told and we observe them. The second condition is the forced condition. Now we tell them that we want you to use your paretic arm in order to perform these tasks. And what we do is that we calculate this non-use index, which is basically forced minus spontaneous condition divided by the forced condition scores. And the non-use index ranges from 0 to 1, with 0 indicating no non-use of the paretic arm and 1 indicating complete non-use of the paretic arm. This study also emphasized that individuals with low motor impairment also show reduced paretic arm use. So what you're seeing on this graph right here on the x-axis, you have the upper extremity Fugl-Muir scores. Again, higher scores indicate lower impairment. And on the y-axis, you have the non-use index. In the top right quadrant that I have highlighted in red there, these are individuals who have low sensory motor impairment but still tend to show higher non-use. This study identified a model which included assessments of motor impairment, so the upper extremity Fugl-Muir, a test of attention, which is the virtual reality lateralized attention test, and self-efficacy as measured by confidence in arm and hand movement, predicting arm non-use in individuals post-stroke. These findings basically highlight that factors beyond sensory motor capacity can play a role in predicting arm non-use. So this preliminary work in 20 individuals with stroke led to a current grant, which focuses on testing 3 different mechanisms that may influence use capacity disparity. And these include the sensory motor, attentional, and apathy or self-efficacy constructs. So that forms aim 1 of the study. Now, beyond clinical and behavioral factors that contribute to use capacity disparity, a lot is not known about the neuroanatomic biomarkers that could predict UCD post-stroke. That makes aim 2 of the study. And finally, for aim 3, we propose and validate a naturalistic VR-based test of use capacity disparity. And I'll talk about this task a little bit more in detail in the next few slides. For today's talk, we are predominantly going to focus on aims 1 and aim 3. Data processing and analysis is still ongoing for aim 2. So here is the inclusion-exclusion criteria. I'm not going to go through all of this, but basically in the study, we want to recruit 100 individuals with chronic unilateral hemiparetic stroke and 25 control participants. For aim 1, we assessed arm use again through the AUT non-use index, which I described earlier. Now, this is a measure that is predominantly done in research settings. But we also assessed arm use through the actigraph use ratio. Basically, we gave participants actigraphs to wear for 5 days on both their arms. We wanted to assess arm use in real life situations. And what we got from the actigraphs is this measure called as the actigraph use ratio, which is basically the total duration in hours of paretic arm use relative to the non-paretic arm. And again, it ranges from 0 to 1, 0 indicating complete non-use of the paretic arm and 1 indicating that both hands were equally used. As a reminder, for aim 1, we wanted to assess the sensory motor, attention, and apathy constructs. So we had a bunch of behavioral assessments that participants completed. Within the sensory motor cluster, we assessed different aspects of sensory motor function, and that included assessing impairment, sensation, proprioception, strength, arm and hand function, and dexterity. We assessed attention using the virtual reality lateralized attention test. We assessed the total score as well as the laterality index score, which is basically a measure of spatial attention. And then we also assessed apathy and self-efficacy using these measures here. Now, why we have 2 different measures? So the AUT non-use index, which like I said is used in research settings, and the actigraph use ratio to give us these values of real life arm use. These 2 variables are correlated with each other. So what you see on the x-axis there is the AUT non-use index. Again, trending towards 1 means greater non-use of the paretic arm. And on the y-axis, you have the actigraph use ratio, where greater numbers indicate more use of the paretic arm. So greater non-use on the AUT was associated with a lower use ratio as recorded by the actigraphs. As I mentioned, this is an ongoing study. As of now, we have recruited 45 individuals with chronic stroke and 19 control participants. So for AIM-1, we wanted to test the prediction of 3 distinct mechanistic accounts, so sensory, motor, attention, and apathy, to see whether these variables could predict use capacity disparity. Our hypothesis for AIM-1 was that beyond motor capacity, cognitive and psychological factors will predict arm non-use post-stroke. So for this aim, we basically applied a lasso regression. Our outcome variables were both AUT non-use index as well as the actigraph use ratio. Our predictors were all of those assessments that we were doing in those 3 domains, and then we also included factors such as the stroke hemisphere and time post-stroke. Now, before I go into the results, just to preface that these are very preliminary analysis that I'm presenting. As I mentioned, this is still an ongoing study and we're going to continue refining these models. So the lasso regression model identified 6 significant predictors of the AUT non-use index. In the sensory motor cluster, we had the upper extremity fugulmare and the box and block difference between the paretic and the non-paretic arm. In the attention cluster, we had the VR-LAT laterality index score that was one of the predictors. In the apathy and self-efficacy cluster, we had both confidence in arm and hand assessment as well as the apathy scale. And then lastly, we also had stroke hemisphere that was one of the significant predictors of AUT non-use index. Combined together, this model had a variance of around 61%. And to evaluate how reliable these variables are in predicting arm non-use using the AUT non-use index, we used something called as a bootstrap lasso approach. The percentages that you see here represent how consistently each variable was selected across the bootstrap samples. So in other words, the higher the percentage, the more reliable that variable is as a predictor. So the upper extremity fugulmare predominantly the VR-LAT laterality index score with high percentages 95 and 99 are reliable predictors. We went ahead and did the exact same thing, but now to predict actigraph use ratio. And again, we had predictors in the sensory motor cluster. So we had the upper extremity fugulmare, the box and block, but in here we also had the Nottingham sensory assessment, which assesses proprioception. In the attention cluster, we had the VR-LAT total score that came up as one of the predictors. In the apathy and self-efficacy cluster, we had the apathy scale. And then again, we had the stroke hemisphere as one of the predictors. We ran a similar bootstrap lasso approach. And we saw variables like the upper extremity fugulmare and the box and block that were significant predictors of use ratio. So to summarize the results of AIM-1, sensory motor function, attention, and apathy may all contribute to use capacity disparity. Predictors may differ for lab-based versus real-life arm measures, as we saw that there were differences in predictors for the AUT non-use index as well as for the actigraph use ratio. And then next steps, like I mentioned earlier, includes refining these models as we collect more data and evaluate the prediction quality of these models. All right, so I am going to move on to AIM-3, which was validating a clinically useful virtual reality tool for assessing use capacity disparity. So in all of my previous slides, I was talking about measuring arm use using the AUT non-use index or through actigraph use ratio to assess this real-life arm use. Now, while these measures have been useful, These measures predominantly assess arm use, but not how efficiently that arm is used. And because the theoretical model, we wanted to assess the impact of factors like attention on arm use, we developed a naturalistic VR task. And the task not only allows us to assess which arm is used, but how efficiently that arm is used by assessing different parameters. And I'm going to briefly introduce this virtual reality task here. So, participants basically performed 3 different conditions. Um, Condition 1 that you see right there, basic array grasp, participants were basically shown a target object and there were distractor objects shown on the shelf. In the basic array, the target and distractor objects were different. So for example, the target might be a fruit, but the distractor objects were household objects. They basically had to look at the target object and go in and grasp the target object from the distractors that they had. In the complex array condition, we made it a little bit more difficult. Now, the target and the distractor objects were from the same category. So, if the target was a fruit, the distractors were also fruit. Participants had to go in and search in the shelf and basically go in and grasp the target object. In the complex array point condition, again, the target and distractors were in the same category, but now instead of grasping onto the object, they had to go in and point to the object. And basically, what we were trying to assess was these effective cognitive and motor demands. So from the basic to the complex grasp, we wanted to see that effective cognitive demand, whereas from complex grasp to complex point, we wanted to see these effects of motor demands because pointing is easier than going in and grasping onto an object. Participants performed 2 blocks of each conditions and these conditions were randomized. And our hypothesis was that we will be able to establish the psychometric properties of this VR task. And we predict that arm choice and movement performance will differ between low and high demand conditions. Just so that it all makes sense, what I was explaining here is in video of what participants do in the VR task. So the lamp was the target and they had to go in and point to the lamp. Right. So to validate the VR task for assessing use capacity disparity, as I said, we wanted to establish psychometric properties, but we also wanted to get a feel of participants' experience in using the VR task. So 42 people completed, 42 individuals with stroke and 19 control participants completed all of the conditions of the VR task. Each participant completed 2 to 3 sessions and each session lasted around 60 to 90 minutes. I do want to highlight that currently this is a long protocol, but the goal is to first validate this task and eventually translate it to clinical settings. In order to get an understanding of participants' experience in using the VR task, we had 2 questionnaires that they filled out. The one is the system usability scale, how usable the system is or how convenient it is to use the VR task. And it ranges from 0 to 100. Greater points indicate the system is easy to use. And as you can see, our control and our stroke participants had very comparable scores, around 78 and 81. We also had the simulator sickness questionnaire because sometimes the VR settings can cause some sort of sickness and we wanted to make sure that participants are comfortable using the VR task. And we had this questionnaire and as you can see, the range is between 16 to 24, 25 for both control and stroke participants. Scores ranging from 0 to 20 indicate that the simulator is not really causing any sickness and our mean points were 18. So it seems like it was quite very well taken by the participants. To assess the psychometric properties, we first started with assessing concurrent validity, which is basically assessing the proportion of paretic arm use in each condition with the AAUT non-use index and actigraph use ratio. And what you're seeing right here are correlations between proportion of paretic arm use in each of the condition with the AAUD non-use index, and we had significant associations with the basic grasp and the complex grasp condition, basically indicating that we are assessing arm use. So greater non-use as measured by the AAUD non-use index relates to lesser paretic arm use in the VR task. We did the exact same thing with the active graft use ratio as well, and now we had significant associations across all the three conditions, indicating that greater use of the paretic arm as measured by the active graft use ratio relates to greater paretic arm use in the VR task as well. We then wanted to go in and assess discriminant validity, which was assessed by comparing the strength of correlations of the proportion of arm use in the VR task with the AAUD non-use index and the upper extremity fugal mirror. Our hypothesis was that the correlation with AAUD non-use index is going to be stronger because these are both measures of arm use compared to with fugal mirror, because fugal mirror is a test of sensory motor impairment. And again, here are the correlations between arm use in the VR task and AAUD non-use index, as well as with the fugal mirror. We had significant associations with AAUD non-use index, but none with fugal mirror. And on running a Fisher transformation, these tests revealed that correlations between proportion of arm use in the VR task correlated better with AAUD compared to the upper extremity fugal mirror for both basic grasp and the complex grasp conditions. Now, this is just a reminder slide that across the three conditions, our aim was to assess this effect of cognitive demand and motor demand on both arm use and motor performance. So you wanted to basically assess the constructive validity of our task, right? We wanted to see the influence of both cognitive and motor demands on arm non-use in individuals with chronic stroke. What you see here is the proportion of paretic arm use across the three conditions in individuals with LCVA and RCVA. Our results indicated that higher task demand showed trends of reduced paretic arm use under both cognitive and motor load, and that there was a significant difference wherein individuals with RCVA showed reduced use of their paretic arm compared to individuals with LCVA. Now, as I mentioned, we saw trends of change in arm use under cognitive and motor load. When we went in and actually looked at this data, these are just individual data plots that I have plotted. And the ones highlighted in red here basically was the pattern that we were expecting to see, right? So we were expecting to see that V pattern where the 3 points indicate arm use in basic grasp, complex grasp, and complex point. And we assume that in the complex grasp condition, we would see reduced use of that paretic arm. So some participants did show that pattern. But what makes the data interesting is that there were some participants who were already at that ceiling and didn't really show a lot of difference across the three conditions. Then we had participants who showed us the complete opposite of what we were expecting. So if you see this one participant right here, very evidently was using the paretic arm more in the complex grasp condition compared to the basic grasp or the complex point, which we think are simpler. And then lastly, there were some participants that were just doing things differently than what we would have expected. All this to say that there was a lot of variability in the way that these participants were performing the task. And we basically want to go in and look at different factors that are associated with this inter-individual variability. So other than arm use, like I mentioned with the VR task, we also wanted to look at parameters that assess motor performance. And we looked at total time, which is basically the sum of reaction time and movement time. And what we saw with these results were that individuals with LCVA and RCVA, the paretic arm total time increased under both cognitive and motor demand. So this was in line with our hypothesis. Now, again, we did some very preliminary exploratory analysis to see if the predictors that we had in the 3 clusters that I showed earlier, if they could predict this decrement in total time across like the cognitive and the motor conditions. So these very preliminary analysis indicated that there were factors that could predict total time decrement under cognitive load. So we had the VR-LAT total, which is a measure of attention that came up. And again, in the side, I have the percentages when I ran the bootstrap lasso. And then there were also predictors that could, there were also variables that could predict total time decrement under motor load, so that difference between complex grasp and complex point. And we got variables such as the upper extremity fugal mirror, the monofilament test, the attention, test of attention, and months post-stroke. Again, as I mentioned, these are very preliminary analysis. As you can see, the prediction power is very low here because there is some signal. As you can see, the percentages are very low, around like 50 to 60%. But we are hoping as we have more data, as we refine these models, we have a signal that might be potentially stronger. So with that, next steps include evaluating the sensitivity of the VR task and also examining potential practice effects or the effect of block or randomization order. So as I mentioned, we saw a lot of variability in how people were performing the task. It could be possible that in addition to factors like the sensory motor impairment, differences in attention, there could be a possible order effect. We want to explore the underlying reasons that contribute to this variability in arm choice under cognitive and motor load. In addition to assessing total time, which is a parameter to assess motor performance, we also want to go in and look at other measures like the reach efficiency and see the effect of cognitive and motor load on reach efficiency. And ongoing data collection will enable us to assess additional aspects of this data and offer more insights into the complex relationship between arm use and task in individuals with stroke. As I mentioned, I'm not really presenting any data from AIM-2, which is to determine the neuroanatomic biomarkers of use capacity disparity, but our plan is to apply lesion symptom mapping analysis to identify neural substrates that could predict use capacity disparity after stroke. And we want to assess both structural and functional connectivity of the white matter tracts and neural networks that underlie sensory motor function, attention, and apathy, and look at their relationship with use capacity disparity post-stroke in order to identify biomarkers. To summarize, measures across sensory motor, attention, and apathy domains have the potential to predict use capacity disparity. The VR task that we proposed enables an assessment of motor performance beyond just arm use under cognitive and motor load. The VR task shows concurrent, discriminant, and constructive validity for assessing use capacity disparity. Motor performance as measured by total time declines under both cognitive and motor load. And these findings are preliminary, and ongoing data collection will help us guide and better refine our conclusions. And with that, I want to acknowledge all of the study participants and their caregivers. I also want to highlight collaborators of the grant. Special shout out to the VR developer, Maxim. And then we were funded by the NIH, the R01 award that was awarded to Dr. Laurel Buxbaum and Shailesh Kantak, by the NIH. And with that, I'm done and I'm open to any questions.